All right, this is the first part of the introduction to the time series models. So a time series basically is similar to a regression function that we've already covered a lot of. However, it utilizes the time variable. And so when we explore the past values of a regression function, we'll call that the lagged values of the explanatory variable. Algebraically, we'll see later, kind of looks like this right here. But before we do all that, we have to expose ourselves to the different types of time series models, because there can be different kinds. Some that utilizes some explanatory variables that only utilize time, some that utilize time, and then other variables that don't, etc. And so we have the finite distributed lag model, the autoregressive distributed lag model, and then the serially correlated errors. The serially correlated errors is not really a type of regression function. It's just kind of a concept that we need to worry about when we utilize the first two. But it is an important part of the time series. Graphically, before we do any analysis of the time series, we have to assume that the data is stationary. Stationary, even by definition, it implies that the data is relatively constant. And so when you see a stationary graph, we have to assume that the value does not stray away from the mean. So assuming like the mean is around here, you can kind of see that even the min and max values of the stationary graph, it doesn't, the range of it isn't too high. And the variance of it isn't high either. And that's what kind of determines a stationary graph. Opposed to these non-stationary graphs where we see clear parts of the trend that definitely don't make the graph stationary, because these min and max points are very far away from the mean, and our variance is not constant. So, well, I guess it is in this case, but our variance, we ideally want our variance to be constant when we determine whether a graph is stationary or not, or when we try to make our graph stationary. And so the just like what we did here, we can always visualize our stationary graph to determine whether it is or not. But there are formal tests called the unit root tests. I'm not going to go over that too quickly, but it does use the p-value. So in the software, it should be pretty simple to run. All right, let's go over the distributed lag model. So this is our first regression function that I'm going to introduce. If you, at first it looks a little unfamiliar, but really the t just stands for the time-based explanatory variable. So x of t, and then x of t minus 1 is the value of 1 unit into the past. So let's say we're looking at the GDP of a certain country. The x of t minus 1 can be or I guess the y can be the income, or y can be the GDP, and then the x can be the income. So the income of the average income of a country, 1 unit in the past. So maybe 1 unit can be like a day. So this can be the income like yesterday. This can be the income today, and 2 days ago, and so on. Just an example. And so in the regression function, we kind of see a similar translation. We just have coefficients that make it different from this one. And so what these coefficients mean is that each time variable have a different value. So we have an intercept as always, but this beta 0 for our current current value time value, it will most likely be different from beta 1, which is the influence from 1 unit into the past. And this is important because most of the time, the coefficients closer to the present are going to be more impactful. And so if you want to measure the change of the output or the dependent variable in relation to a past variable, we'll just take the derivative of y in respect to a specific x variable. All right. So the way the time series slopes are interpreted can be a little confusing. Let's say in a regression output, we see that the slope of an explanatory variable 2 units into the past, right here, 2 units into the past is 420. That's the slope. And so the way we can interpret this is a 1 unit change at the 2 units in the past is actually a 420. This right, I think this is minus 420. A minus 420 units of change into the future. So it's not necessarily saying a 1 unit change in the 2 units into the past has a minus 420 impact into the y output for that t minus 2, but it's saying t minus 2 excuse me, a 1 unit change there is will have this kind of impact into the present. Similarly, if you interpreted 1 unit at the current time, then it's almost like we kind of shifted 2 time periods forward. And so we can kind of interpret that as 1 unit change at the current time will result in a minus 420 change into the 2 units into the future. So from what I've analyzed from these type of things, it is a bit confusing. So it becomes easier when we actually do some real hand stuff on this type of stuff. But for now, I think it's just something good to know. Yeah, good to know down the road, but it is difficult to interpret in our first attempt. All right, and so another important part of the time series model is determining our lag length. So let's say let's look at this regression function here. Let's say let's ignore this part and say our regression function goes up to only two units into the past. And so a question we might ask ourselves is, how do we know we need to cut it off at there? Like, how do we know if 3 units into the past is appropriate, or 4 units, or even 1 unit? And so the way we determine that is we use similar to the model specification method, we can use the R squared, the adjusted R squared, ideally, and then the AIC and BIC. And so recall I'm not sure if I have it here, but yeah, right here. So recall that these use the sum of squared errors, the n part of the function to kind of determine the best type ideal model. So similar to the model specification, the time series model kind of chooses our lag length based on these minimization of sum of squared errors and most, like, I guess our sample size will always be the same. So the one that minimizes the sum of squared errors. So usually it will be a low, our lag time values will be relatively low because the variables that are very deep into the past, they'll have a very little to no impact on the current output of y. Okay. And so the most common problem that occurs in time series data is called what we call autocorrelation. So in a regular data that are not time based, we discussed heteroscedasticity, right? And so similar to autocorrelation, it kind of follows the same properties. Where like we want our variance to be constant and whatnot. And so autocorrelation, we don't necessarily get the best graphical view, but we get this problem of one value being too similar to having too much of an impact over the other, just because they are how do I say this? They're basically too similar. Um, so just like heteroscedasticity and autocorrelation, you might, I've always asked like, well, why is this a problem? And the it ultimately results in that we can't minimize our sum of squared errors, and that is in the end of the day our goal to get our best fitted model. The fact that I think the fact that one value is being too correlated to another past value isn't necessarily the problem. The problem is that kind of aspect of the autocorrelation is what makes our minimization method unreliable. Just like heteroscedasticity, the autocorrelation has a test method where the null says there is no autocorrelation, the alternative saying there is. And so the first method I'm going to introduce you to is the utilization of a parallelogram. And so we use our z statistic here using our correlation value minus 0 because that's our null hypothesis, divided by the square root of 1 over n. And what this simplifies to is the equation right here. And then so ultimately, if this is greater than the critical value, we can reject the null hypothesis and conclude that there is autocorrelation. Now, obviously, compared to heteroscedasticity, autocorrelation, we need to kind of determine that one by one because some values may be autocorrelated, others may not be. It's a finite number of values we're going to use. Or finite, but very limited or short. All right, so in an example, let's say we have a 64 sample size and we're given the correlation of these past values of 1 unit into the past being 0.03, 2 units into the past being 0.02, and 3 units into the past being 0.01. And so with that, we need to determine the path lags which of the path lags that are significant to autocorrelation. So using this formula right here, we can square root this 64, which is an 8, and then we could multiply the correlation values that we were given in the example. And then this is what this is our correlation values we get here, or our autocorrelation values we get here. This is my bad. This isn't our actual autocorrelation value. This is our R statistic or correlation statistic. So visually, if we see here, 0.24 passes the threshold. Now the threshold isn't always 0.2. That's just an example I gave. But usually if we do by software, it will give an absolute threshold, both in the positive and negative, because the correlation can also be negative. But our first value is over the threshold, If it was over here, that would be fine too. But because it passes a threshold, it's over 0.2, the correlation. And so we conclude that the first pass value has autocorrelation, but these two don't pass the threshold, the second and third pass values. And so they're not significant to autocorrelation, which means only the first value is needed to correct for. And so this example I gave is not really a coincidence to real life applications or examples where, again, the first, usually the earlier, more recent past values will have a bigger impact into the current value because they are bigger determinants to what our future outcome might be compared to our older values that are more likely irrelevant. But that's it for now. In the next video, I'm gonna go over the second part of the time series model. But this is, I think, a good overview